Welcome to the second video of Chapter 16. In the first video, we looked at vector fields and gradient fields. In this video, we're going to look at line integrals. Now, before we even start talking about line integrals, I just want to give you an idea of what the rest of this unit will look like. We have two integrals that we haven't learned how to calculate yet. One is line integrals, and then later in a few sections, we're going to talk about surface integrals. Both of these have large applications for us in real life, and so over the course of the rest of this unit, we're going to look at those two kinds of integrals, different ways to calculate them, and then their applications. So before we take a look at line integrals, let's talk about what we already know how to do. We've talked about single integrals, where we've integrated over an interval. Then we learned how to calculate double integrals, where we integrated over an area and two space. Triple integrals, we integrated over a solid in three space. So what we're going to do today is we are going to integrate along a curve. And so just to give you an idea of why we're going to do that, it helps us to find mass, it helps us to have a mathematical definition of fluid flow, it helps us with force. So those are our three main applications. So let's start by talking about what is a line integral. Okay, so what we have off to the right is we have some curve C that's defined parametrically. X is a function of t, y is a function of t, and t is between a and b. And so what we see here is t, each of these points is different values of t, is defined between a and b. If we take some value of t, like this one right here, that gives us a point on the curve. Another value of t gives us another point on the curve. And so what we're going to be looking at is we're going to be summing up the function values, and then this delta s sub I is the length of the subarc. So let's take a look then at what that means in terms of a line integral. If f is defined on a smooth curve C, again, C is defined parametrically, then the line integral of f along C, so the line integral of f along C is the limit as n goes to infinity of what we saw above, the function value times the length of the subarc. Now, some things I want us to look at real quick before we keep going. This C is not a bound. What that little c tells us is that this is a line integral. Other way or other piece that's going to come along with a line integral is this ds, and it's a little s. We're going to look at integrals later that have a big S. So c is not a bound. It tells us it's a line integral along with ds. Now, in order to talk about how we calculate that, we need to recall how to find arc length. So if we recall, arc length is the integral from a to b of the square root of dx dt squared add dy dt squared dt. So then, what that tells us is the line integral along the curve C, ds. The way we calculate this is this becomes a regular integral from a to b of f of x of t, y of t, multiplied by that arc length, that dx dt squared, add dy dt squared, all of that dt. And of course, this is a similar idea in three space. And if you recall, we saw this in earlier units when we looked at arc length. ds dt is that arc length formula. So again, dx dt squared, add dy dt squared, which tells us then that ds is just that same square root times dt. So that should explain why this ds turns into that square root dt is for this reason below. So now that we see how to calculate a line integral, let's look at some examples. Example number 1, evaluate that line integral where c is the upper half of the unit circle. So again, I know this is repetitive, but I want to really drill it home. The way we know this is a line integral is we are integrating along some curve, and then we have this little ds. So the first thing that we would want to do is draw out what is our curve c. So again, c is the upper half of the unit circle. So that would be this. This is our c. So in order to calculate this line integral, we're going to need a parameterization for that curve. So this curve we can write as x is cosine t and y is equal to sine of t. So then, if we want our line integral of c of 2 add x squared y ds, what that's going to turn into is t is going to go from 0 to pi. And then we have f of xy, right? So this is our f. So we're going to need to substitute in our parameterizations for x and y. So that'll be 2 add cosine squared t sine squared t. Then we're going to have our arc length. So the derivative of cosine is negative sine. So we're going to get negative sine of t squared. The derivative of sine is cosine, 1 squared dt. So then hopefully we can see that this length is just 1. So this is going to be 2 add cosine squared t. Oh, it's just sine t. Sorry, I don't know why I put a squared there. dt. So then integrating, this will give us 2t, subtract 1/3 cosine cubed t, being evaluated from 0 to pi. And ultimately, that simplifies to 2 pi add 2/3. Okay, let's take a look at another example, one that is a little bit more involved. Evaluate the line integral of x ds, where c is the portions of y equals x and y equals x squared from 0, 0 to 1, 1. Okay, so I'm going to go from 0, 0 to 1, 1, and we have y equals x, and then we have y equals x squared. So here's our y equals x, here's our y equals x squared, and I'm going to tell you we first go along y equals x, and then we come back along y equals x squared. So in this case, we actually have two curves that we need to consider. So we're going to call that first curve y equals x, and we're going to call the second curve y equals x squared. So I'm going to start along C1, which is y equals x. So in this case, this is a pretty easy parameterization. X I can call t, y I can call t, so then t is between 0 and 1. So then we are integrating from 0 to 1. Remember, our function is just x, so in terms of t, that's just t. And then our arc length, we're going to have the square root of x of t squared, add y of t squared dt. So this is integrating from 0 to 1 of t root 2 dt. And if you integrate that, you get root 2 over 2. So that was our first curve. Now let's go along our second curve, and that is the one y equals x squared. So we're going to be tempted to say, oh, this is an easy parameterization again. I'm going to use x equals t, y equals t squared. And let's see if that works. Well, if we plug in t equals 0, that would be the point 0, 0, and that would take us to the point 1, 1, which is not what's happening. If we look at our curve, we're starting at 1, 1, going to 0. So that parameterization is actually not going to work. Instead, what we're going to need to do is if we call x 1 minus t, and y then is 1 subtract t quantity squared, with t being from 0 to 1. Now if we plug in 0, we're starting at the point 1, 1. If we plug in 1, we're going to the point 0. Okay, so now getting ready to parameterize. This is 0 to 1, not parameterize, getting ready to calculate our line integral. 0 to 1, our x is 1 subtract t. And then for our arc length, we get 1 add 4 times 1 minus t quantity squared dt. Okay, so let's be smart here. Let's not multiply all of that out. What's going to be most helpful to us is if we do a u substitution. If we call u everything that's under the square root, our du then is going to be 4 times 2 times negative 1 times 1 minus t to the first, or of course negative 8 times 1 minus t. So going back and integrating then, since we don't have that 8, it's going to give us a negative 1/8. And then we have 2/3 times 1 add 4 times 1 minus t squared to the power 3 over 2, being evaluated from 0 to 1. And if you just trust me on this one, you end up with 1 over 12 times 5 to the 3/2 subtract 1. So ultimately, where all of this leads us to is that our line integral over the curve C of x ds is going to be equal to root 2 over 2 add 1/12 5 to the 3/2 subtract 1. Okay, as a quick note, right now we have what are called arc length parameterizations. So what that tells us is that orientation, actually, I'm sorry to tell you, doesn't matter. This is very important though. Orientation is going to matter later. And we will talk about when that is. So what I mean by that is if we return up to all this work that we did in blue, the first thing that we considered is for that second curve, we considered x equals t and y equals t squared. And we said that wasn't appropriate because we were moving in the wrong direction. We were going from 0, 0 to 1, 1 when we wanted to go the reverse direction. Well, if we instead used this parameterization, so from 0 to 1 of t multiplied by 1 add 2t quantity squared dt, we would end up with 1/8 times 2/3 add 1 plus 4t squared to the power 3 over 2, being evaluated from 0 to 1. And what I will tell you is you get that same quantity. So we still get the 1/12 5 to the power 3 over 2 subtract 1. So again, what I'm telling us is that the orientation doesn't matter in this case. So the way that we take the curve doesn't matter, but it will matter later. And again, we will talk about when it matters later. So now that we have an idea of how to calculate these line integrals, we need to talk about what does this actually mean? So what do these numbers actually represent? Okay, so the question again is, what does this all mean? Well, it depends on how you're interpreting the function f. Let's say that f of xyz represents density. The line integral then, there should be a z here, the line integral calculates for us the mass of a thin wire that is shaped like C. Instead, if f of xy is a curve, then the area underneath the curve can be given by the line integral of x of fy, f of xy ds. So for example, what I mean by that is if we have some curve like this, so this is our f of xy, so that's some surface, and then if we have some curve C on the xy plane, our line integral will give us this whole area as if we put C up onto the curve. Okay, so far what we've done is we've calculated line integrals with respect to arc length. That's what that ds means. Sometimes though, we calculate integrals with respect to x or y, and so you'll still see that C for a line integral, but then you're going to see dx and dy. And so if it's dx, it's going to start out the same. We're integrating from a to b it's going to be f of x of t, y of t, and then instead of multiplying by arc length, you're going to multiply by x prime of t dt. Likewise, if you're integrating over y, again, a to b, we have f of x of t, y of t. This time we're multiplying by y prime of t dt. And then, of course, sometimes you're going to see them together, in which case you're integrating with respect to x and y. Okay, so let's see an example that looks like that. We are evaluating that line integral two different ways. The first way is along the curve C1, and the second way is along the curve C2, where C is as shown. Okay, so we are going to start along C1, and C1 is the line segment that goes from -5, -3 to 0, 2. So first thing that we're going to have to do is we're going to have to be able to write that parametrically. So we've done this before. Hopefully you remember how to write line segments parametrically. General form is 1 minus t r naught, so that's the starting point or the vector for the starting point, plus t times r1, t being from 0 to 1. Okay, so r naught is that starting point, -5, -3. And then we are going to the point 0, 2, which means that we can write r as 1 subtract t times -5, -3, and we are adding t multiplied by 0, 2. And so to simplify this, we get -5, add 5t, add 0, and 3t, add 2t, subtract 3. So then that first curve is -5, add 5t, 5t subtract 3, where t is between 0 and 1. Okay, so what we're going to have to use then is x is 5t subtract 5, which means dx is 5 dt. Our y then is 5t subtract 3. Our dy then is 5. And again, t goes from 0 to 1. While I'm at it, I'm also going to look at that second curve. So that second curve, you can see, same 2 points, but now it's along the curve 4 minus y squared. So what we can do is we can let y equal t. So then x is 4 subtract t squared. And t then, or y, is going from -3 to 2. So let's pause and just see, does that make sense? If we call y t, x then is 4 minus t squared, and our t is just the bounds for y, -3 to 2. Okay, so what that gives us then is dy is just 1 dt, and dx then is -2t dt. Finally, we are ready to calculate, and if we remember, this is the line integral that we are looking to calculate. If I go back to C1, I'm integrating over the curve C of y squared dx, add x dy. So I'm going to be integrating from 0 to 1. Y squared is going to be 5t subtract 3 quantity squared, and then my dx is 5 dt. X is 5t minus 5. dy is 5 dt. Okay, so then if I go to simplify this, I'm going to factor out a 5. So this is 5 integral from 0 to 1. And if I multiply everything out and combine like terms, I get 25t squared, subtract 25t, add 4 dt. So now integrating, I'm going to have 25 over 3t cubed, subtract 25 halves t squared, add 4t, all from 0 to 1. And finally, what that gets us is the line integral along that first curve is -5/6. Okay, now we have to evaluate this integral along the second curve. So again, it's the line integral of c y squared dx add x dy. So what this becomes is we're integrating from -3 to 2. Y squared is t squared times -2t dt. And then add to that x, which is 4 minus t squared times y, dy rather. Okay, if I multiply everything out and I combine like terms, I'm integrating from -3 to 2, and I'm integrating -2t cubed, subtract t squared, add 4 dt. Okay, and finally integrating, I get -1/2 t to the 4th, add 1/3 t to the 3rd, add 4t, from -3 to 2. And if you trust me, I will tell you that ends up being 5/6. So the line integral along the first curve was -5/6. Along the second curve, though, was 245/6. So this is really important. Let's look at the next page to summarize what this told us. So what this tells us is that path matters. Path matters, not just the endpoints. So when we calculated the line integral along C1, we got one value. Along C2 gave us a different value. So the path matters, we can't just pay attention to the endpoints. Quick note before we go on and do some more calculations is that evaluating a line integral in 3-space is almost exactly the same as 2-space, you just have another variable. Since we're having so much fun with line integrals, let's do 2 more examples in 3-space, and then we will move on to the next part of the video. So example 4, again, we are evaluating a line integral, this one ds, where c is the curve that is given to us. And t is from 0 to 2 pi. So our line integral then of y sine of z ds can be written from 0 to 2 pi. Y is just sine of t. Sine of z then is another sine of t. And then we have our arc length parameterization. So the derivative of cosine of t is negative sine of t, and we're squaring it. Derivative of sine of t is cosine of t, and we're squaring it. Derivative of t is 1. So what this gives us then is the integral from 0 to 2 pi of sine squared t times the square root of 2 dt. Okay, the reason I wanted to see this example is I was curious if we would remember the substitution for sine squared t, because right now we can't integrate this. So from pre-calc, the substitution for sine squared is 1/2, subtract 1/2 cosine of 2t. And then if I bring that root 2 out, integrating from 0 to 2 pi dt. I'm not going to go through integrating that. I'll just tell you the answer ends up being root 2 pi. Okay, we have one more example that we are going to do in 3-space, and then we will move on to our next objective. So we are evaluating this line integral where c consists of the line segment from that point to that point, and then a vertical line segment from that point to that point. So I'm not going to draw this. I'm just going to start by writing our 2 line segments parametrically. So our first line segment we can write as 1 subtract t times the starting point of 2, 0, 0, add t times our ending point of 3, 4, 5. So that R1 of t then, once we simplify everything, ends up being 2 add t, 4t, and 5t, t from 0 to 1. Okay, so getting on now to the actual line integral part of it. I'm going to do a lot of this in my head, so hopefully you can follow me. This ends up being the line integral from 0 to 1 of 4t, dx is 1 dt. z is 5t, dy is 4 dt, and then x is 2 add t, and dz is 5 dt. And that, I'm just going to tell you, ends up being 24.5. Okay, so now along C2 being the vertical line segment that goes from 345 to 340, starting in a similar way, we get 1 subtract t multiplied by the vector for our starting point plus t times the vector for our ending point. And I will tell you that ends up being, no surprise here, 3, 4, 5 minus 5t. Okay, so then we get the integral of 0 to 1. Y is 4, dx is 0 dt, z is 5 minus 5t, dy is 0 dt, and then x is 3, and dz is negative 5 dt, and that ends up being negative 15. So our final answer comes when we add those two together. 24.5, add negative 15, and we get an answer of 9.5. Okay, that was the first objective. First objective was how to calculate a line integral. So we're going to move on and build on with that. Now that we have the basics of line integrals, what we're going to be looking at is line integrals of vector fields. We're going to start by recalling how to calculate work. We took f and we dotted it with d. So what we have now is, let's suppose that we have some vector field and the x, y, and z components are all going to be functions of some type. And that vector field is a continuous force field. So let's say maybe it's a gravitational force field, maybe it's an electric force field. What we want to do is we may want to calculate the work done in moving a particle along a smooth curve C. So this leads us to our next objective and our next definition. Let f be a continuous vector field defined on a smooth curve C given by r of t. Then the line integral of f along C, it's going to be C of f dot dr, so that's different. That's going to be different. The way we calculate this is the integral from a to b of f of r of t dotted with r prime of t dt. So these are two vectors, so we're taking the dot product. Alternately, this can also be written as the line integral of f dot t ds, still a little less. And what this does is it calculates work. It calculates work. And so, of course, we're going to do an example that has to do with work. Example 6, find the work done by this vector field f on a particle moving along the helix given by this r, where t is between 0 and 3 pi. So work, we're going to calculate as the line integral of f dot dr. So we're going to need r prime of t. We have r above. R prime of t is going to be negative sine of t, cosine of t, 1. We are also going to need f of r of t. So what we're doing is we're taking these equations for x, y, and z and substituting them in. And so when we do that, we get negative 1/2 cosine t, negative 1/2 sine of t, and 1/4. So our work then, we have the integral from 0 to 3 pi, and we're going to take that f, that negative 1/2 cosine t, negative 1/2 sine of t, 1/4, and we're going to dot it with negative sine of t, cosine of t, 1, and then we have dt. Okay, so that ends up being 1/2 cosine t sine t, subtract 1/2 sine t cosine t, add 1/4 dt. Ooh, how convenient. So those trig functions, or trig expressions really, are going to drop out. And so this gives us a work of 3/4 pi. And again, that is the work that is done by this vector field, maybe this force field, on moving some particle along this curve. Okay, we've got a little bit to go still. So I know that this has been a long video, but stick with me. We got a few more examples together, and I will try to keep them. Okay, before we move on to our last two examples, there is a quick remark for you. Let's say we are calculating the line integral along the curve C of f dot dr. If we then go along the same curve but the reverse direction, we are going to end up with the opposite sign. The opposite sign. So in words, what this tells us is if we reverse the path, the work will be the opposite value. And so sometimes that fact may come in handy. Sometimes it might be easier to take the path one direction versus another, and then you can reverse the direction. It's just going to give you the opposite sign. Okay, so let's flip the page and look at our second to last example. Example 7, evaluate this work integral. We're given f, we're given c. Okay, so let's get started. R then is t squared, t cubed, which means that r prime is 1, 2t, 3t squared. Our f of r, again, that just comes from plugging these in for x, y, and z into f. That gives us t to the third, t to the fifth, and t to the fourth. So if we're calculating work then, our f dot dr, it's going to be the integral from t from 0 to 1, and we're taking f, which is that t cubed, t to the fifth, t to the fourth, and we are dotting it with r prime, which is 1, 2t, 3t squared, dt. This ends up being the integral from 0 to 1 of t cubed, add 5t to the 6th dt, which finally gives us an answer of 27/28. Okay, we have one more note, one more example, and that's it. So, last note, let's consider some vector field, again, where the x, y, and z components are some functions of x and y. And our r then, we have x as a function of t, y as a function of t, and z as a function of t. Our line integral then of f dot dr becomes p, q, r dotted with x prime of t, y prime of t, z prime of t, dt. So what that becomes then is that there's an integral up here from a to b. So this becomes the integral from a to b of p dot x prime of t, add q times y prime of t, add r times z prime of t, dt. And so that can be written as the line integral of p dx, add q dy, add r dz. And so if you see that, that's just work. If you see that, that's just work. Okay, this last example I threw in here because it's hard to integrate. I highly suggest that you watch this example. I'll try to be quick, but it's going to potentially introduce you to an integration method you haven't seen before. So again, we're calculating work. F is this vector field, C is R as given. So if we write F in terms of R, that gives us cosine X, sine X. So if we want our work, our C line integral along the curve C of f dot dr, it's going to be our integral from -1 to 2 of cosine t sine t. Yeah, so these should Sorry, poor notation. This should be a t above, not an x. And we're dotting that with r prime, which is 1, 2t dt. So this gives us then the integral from -1 to 2 of cosine t, add 2t sine of t dt. If we integrate then, cosine of t, that's an easy one, right? We just get sine of t. The issue is what we have here, integrating 2t sine of t. Now, what your options are, of course you could do integration by parts. I'm going to be honest, I don't love integration by parts, and so I don't do it unless I have to. So your other option, and I can't remember if I've showed us this in a video or not, is what is called tabular integration. So here's how tabular integration works. We have 2t, and we're multiplying by sine of t. So we're going to split it up into two parts. We're going to take one that we're going to differentiate, and we're going to take one that we integrate. The part that we differentiate has to go to 0. So I'm not going to differentiate sine of t because it's never going to get to 0. So if I take 2t, take a derivative, I get 2, take a derivative, I get 0. So then if I integrate sine of t, I'm going to get negative cosine t. I integrate again, I get negative sine of t. So here's how it works then. We go on a diagonal, opposing signs. So you start with adding, and then you're going to subtract the next. So this ends up with 2t multiplied by negative cosine t, and then we are going to subtract 2 times negative sine of t. So that gives us negative 2t cosine t, add 2 sine of t. So that is the rest of our integration. So we have negative 2 cosine t, add 2 sine of t, and then all of this we're integrating from -1 to 2, or we're evaluating from -1 to 2. We've already integrated. That ends up being 3 sine of 2, add 3 sine of 1, subtract 4 cosine 2, subtract 2 cosine 1. So that is our answer, and if you wonder what that quantity is, it's about 5.84. Okay, you cannot use tabular integration every time you are required to do integration by parts. Tabular integration only works if one piece of your expression can get down to 0, right? And so if you're thinking, I want to integrate something like e to the t sine of t, you can't use tabular integration there. E to the t is never going to differentiate down to 0. Sine of t is never going to differentiate down to 0. So integrating this expression in green, you would have to do integration by parts. Okay, I know that was a lot for us. In coming videos, what we're going to be doing is we're going to be sticking with line integrals, and we're going to be talking about some other applications or how to calculate them more efficiently in some cases. So thank you for sticking with me. If you have any questions, please make sure you ask. Until next time.